In 1997, a microphone on the floor of the Pacific Ocean picked up a sound so loud it was detected by sensors nearly 5,000 kilometers away, a sound that no scientist could identify. They called it the bloop, and then it stopped, and it never happened again. What made it is still not fully understood. The ocean covers 71% of the Earth's surface, and yet we have mapped less than 25% of its sea floor. The deep ocean is, by a significant margin, the least explored environment on the planet. More humans have walked on the moon than have descended to the deepest point in the sea. And from within that unexplored darkness, we have been hearing things we cannot explain. Not one sound, not two. A catalogue of anomalies, each one recorded, each one real, and several still without a definitive answer. To understand what we might be hearing, we need to understand the system listening. During the Cold War, the United States military installed a classified network of underwater microphones across the floor of the Atlantic and Pacific Oceans. Its name was SOSUS, the Sound Surveillance System. Its purpose was to track Soviet submarines. But sound travels differently underwater, much farther, much stranger. At a certain depth in the ocean, a layer exists called the SOFAR channel, the sound fixing and ranging channel. At this depth, temperature and pressure combine to create a kind of acoustic corridor. Sound entering this channel becomes trapped inside it. Instead of spreading outward in all directions and fading, it travels horizontally, sometimes for thousands of kilometers, with almost no loss of energy. A whale call made near Iceland can be detected in Bermuda. In 1991, when the Cold War ended, NOAA, the National Oceanic and Atmospheric Administration, was given access to the SOSUS network. Scientists began using it to listen to the ocean, and almost immediately, they began to hear things they had never expected. The first anomaly they named was Julia. Recorded in March 1999 by the Equatorial Pacific Hydrophone Array, it lasted 15 seconds. It was loud enough to be heard across the entire Pacific sensor network. The sound resembled a long rising moan. Its origin has never been confirmed, though one hypothesis suggests it was a large iceberg running aground somewhere in the Antarctic. Then came Upsweep. First detected in August 1991. Unlike the others, Upsweep was not a one-time event. It came back seasonally, every year, for years. A long, sweeping rise in frequency, repeated in a pattern. Its source was eventually traced to an area of volcanic activity near the Pacific-Antarctic ridge. But what specific mechanism produces the sound in exactly that shape, that precise rising sweep, is still not completely understood. Then there was slowdown. Recorded in 1997, a signal that steadily decreased in frequency over 7 minutes. It was detected simultaneously by 3 separate sensor arrays spread across the eastern Pacific. Whatever made it, it was enormous in scale. Slowdown has never been convincingly explained. And then, the bloop. The bloop was recorded in the summer of 1997. It was louder than any of the others. It was picked up by sensors nearly 5,000 kilometers apart. Scientists who first heard it sped up the recording to make it audible to human ears. What came out was something resembling an enormous organic-sounding call. Low, rising, then cutting off. For years, it had no explanation at all. In 2012, NOAA released a statement suggesting the bloop was likely produced by an ice quake, the cracking and fracturing of large ice sheets in Antarctica. The signal profile was said to loosely match known icequake signatures. Many researchers accepted this. Some did not. Because the sound's profile, its shape, its frequency pattern, the abruptness of its onset, and its cutoff does not match any documented icequake in the existing literature with full precision. The bloop remains officially categorized as likely explained, not confirmed, likely. When the bloop was first detected, before any geological explanation was offered, researchers noted something important. Its original location was near the southern Pacific Ocean, very close to the geographic coordinates of a place called Point Nemo. Point Nemo is the most remote location on Earth, the point in the ocean that is farthest from any land in every direction. The nearest humans to anyone standing at Point Nemo are typically the astronauts aboard the International Space Station. It is also, for reasons that remain incompletely understood, one of the quietest regions of the ocean. Almost nothing passes through it, which means when the bloop appeared there, it stood against near-total silence. Could a biological source have produced a sound of this magnitude? The question is not as simple as it sounds. The blue whale is the loudest animal ever recorded. Its calls can reach 188 decibels and travel hundreds of kilometers through the SOFAR channel. But the bloop, at its source, was estimated to be significantly louder than any known blue whale call. And its frequency pattern was different, lower, with a rising profile that does not match the recorded calls of any known species. There is no confirmed biological candidate for the bloop, but there is a reason that question is still worth asking. Scientists estimate that somewhere between 91 and 95% of deep-sea species remain undiscovered. That is not a casual estimate. It comes from comparing the rate of new species discovery over recent decades against statistical models of species distribution. The deep ocean is not an empty place. It is a heavily populated one that we have barely begun to sample. New species of large deep-sea animals continue to be found. In 2021, a new species of beaked whale, a genus entirely unknown to science, was confirmed from acoustic recordings and a small number of physical specimens recovered from strandings. The animal was not confirmed until 2021. It had presumably existed in the deep Pacific, entirely undetected, for as long as whales have existed. In 2023, a previously undescribed species of large shark was identified from specimens collected in the deep waters off the coast of New Zealand. The ocean does not stop producing new large animals simply because we have stopped expecting it to. And the deep ocean imposes its own conditions on size. In an environment with no light and extreme pressure, the usual constraints on body scale shift. Gigantism is not unusual in the deep sea. It is common. Giant squid, giant isopods, giant amphipods. Some organisms in the deep reach sizes several times larger than their shallow water equivalents. This phenomenon, called deep sea gigantism, is real, documented, and poorly understood. The total volume of the deep ocean, below 200 meters, is approximately 1.335 billion cubic kilometers. Of this, the fraction that has been directly observed, sampled, or visited by any instrument is vanishingly small. A 2022 study estimated that the area of seafloor directly imaged at high resolution by remotely operated vehicles amounts to roughly the size of the state of Rhode Island, in an ocean that covers 71% of the Earth. The SOSUS network and its successors give us ears, but no eyes. We can hear that something happened. We cannot see what made it. Even when a sound is triangulated to a location, reaching that location, if it lies in the deep open Pacific, far from any port, requires a research vessel, weeks of transit time, and equipment capable of operating at depths where the pressure is hundreds of times greater than at the surface. Most such deployments never happen, not because scientists do not want to investigate, but because the cost and logistics are prohibitive. In this environment, a sound can appear, be recorded, be studied for decades, and still remain without a definitive answer. Not because the answer does not exist, but because we do not yet have the tools to go and find it. Normally, if a large animal exists, we expect to eventually find evidence of it. But the deep ocean floor is, in most regions, one of the worst possible environments for fossil preservation. The pressure, chemistry, and microbial activity at depth destroy organic material rapidly. Most organisms that die in the deep ocean are consumed entirely before they can sediment. Almost nothing fossilizes there. What this means in practice is that the absence of fossils from the deep ocean tells us almost nothing. We would not expect to find them, even if large animals existed there in significant numbers. Occasional exceptions surface. Literally, deep-sea animals strand on beaches. They are caught in deep-water trawls. They are spotted near the surface during rare vertical migrations. The giant squid, Architeuthis dux, was unknown to science as a confirmed living animal until 2004, when the first photographic evidence of a living specimen was obtained. Until that point, we knew it existed only from dead specimens and partial remains. It had always been there. We had simply never seen it alive. In 1997, something in the deep Pacific made a sound loud enough to be heard across an ocean. We sped it up to listen to it. We triangulated where it came from. We studied it for 15 years before offering an explanation, and even that explanation carries the word likely rather than confirmed. The bloop may have been an icequake. Slow down may have been a geological event. Julia may have been ice. These are the most probable answers, and probability matters. But the ocean is still making sounds we do not understand. New anomalies are still recorded, and 95% of the deep sea has never been seen by any human eye or instrument. We are not listening to an empty place. We are listening to the largest unexplored space on the surface of the Earth. A place with its own physics, its own rules about size, and its own complete catalogue of life that we have barely started to write. And somewhere in that catalogue, something was loud enough to cross an ocean. We just don't know what.